So here we have, we're talking about kinetic energy, potential energy, and work. So my name is Antara. You can stop me at any point if you have any questions, just unmute yourself and I can try and answer your questions. So first of all, I just want to talk about what is basically energy and what is work. So energy is the ability for something to do work. But work is when you basically transfer energy, and also it can be in terms of energy or in terms of forces. So in terms of energy, it's like the transfer of energy, but in terms of forces, it's when a force is acting in a certain direction and the object is moving in the same direction as the force is acting. That's when work is done. And usually the standard unit for energy and work is joules. And on the right-hand side, I just have a picture of showing different forms of energy we may know of in real life. So electrical energy, like in a battery, or magnetic energy in a magnet, or from a fire, you get thermal energy, and through reaction, you get chemical energy, and nuclear energy, like in stars, and of course, light. And then, of course, there's potential and kinetic energy, which are the two big ones that we'll be focusing on today. So I will move on to the next slide, where we're going to talk about what is kinetic energy. So kinetic energy is basically energy that is due to an object's motion. So since it's due to an object's motion, it is in association with the object's mass, and not just the velocity, but the velocity squared of the object. So basically, when something is moving, it has kinetic energy. And on the right side, I have a formula for kinetic energy, which is 1/2 mv squared, where m is the mass of the object in kilograms, and v is the velocity of the object in meters per second. And when you combine the units for the mass and velocity with those terms, you get kinetic energy in joules, which is our standard unit of energy. So kinetic energy is basically directly proportional to the mass of the object and the velocity squared of the object. Now here I have an example. So if we want to read it real quickly, I am going to switch into a notebook so I can write this example down with you guys. So I have an African elephant that has a mass of 6,000 kilograms and is running at a velocity of 10 meters per second and is charging at a tree. So how fast would a 1 kilogram cannonball travel if it had the same kinetic energy as the elephant? So I'm going to go ahead and switch into I'm going to switch into my notebook. So I'm actually going to turn off my camera because I have to turn my laptop around to write on it. And I'm going to switch the notebook to work this out with you guys. So here we're talking about kinetic.
I can learn to understand you much better if I can get familiar with the way you talk.
So here I am going to work on an example with kinetic energy. So basically, I want to draw an elephant. So I'm just going to draw a box as the elephant, and it's moving in some direction towards this tree. It's going at 10 meters per second, and the weight of, or the mass of this elephant is 6,000 kilograms. So M equals 6,000 kilograms. And and the velocity equals 10 meters per second. So first, we want to try to find the kinetic energy of the elephant. So this is I'm just going to write elephant just to know. And we also have, in the other scenario, the cannonball moving, and we want to find what is its velocity. If they have the same, and the mass of this cannonball is 1 kilogram. And we want to find the velocity of the cannonball if the kinetic energy of the elephant is equal to the kinetic energy of the cannonball. So let's first, we have our formula for kinetic energy is equal to 1/2 mv squared. So we have mass and we have velocity for the elephant. So we can easily find the kinetic energy of the elephant. So let's go ahead and do that. I'm just going to plug in the mass, which is I incorrectly wrote it, 6,000 kilograms. 6,000, and I like to write units a lot of times, kilograms, just to know I'm keeping track of them. And then the velocity is 10 meters per second. And the units are the same as in the formula that I had shown on the PowerPoint slide. So our formula should come out to have the units of joules for kinetic energy, and it's squared. We can't forget the squared. So I'm just going to plug these numbers into my calculator. So 1/2 times 6,000 times 10 squared. And I get 300,000 joules. Now 300,000 is sometimes a really big number to work with. So, but we're going to keep it in joules so we can plug it in to the same formula, but for the cannonball. So we know this is the kinetic energy of the elephant, but we know that it has the same kinetic energy as a cannon. So we're going to go ahead and use the same formula, but try to figure out a different variable in the formula. So we're going to rewrite this equation. We have kinetic energy of the cannon equals 1/2 mv squared. And we have to remember it's a cannon. So we have the kinetic energy of the cannon. We have the mass of the cannonball, but we're trying to find the velocity. So let's go ahead and plug in the kinetic energy of the cannon, which is 300,000 joules equals 1/2 times 1 kilogram v squared. So we're going to solve for this variable, v, basically. So what we're going to do is 1 kilogram, it really cancels out because it's a 1. So we're going to go ahead and divide by 1/2 on each side. And we get 600,000 joules equals v squared. And now to get v alone, we can just take the square root on both sides. And we should get the square root of 600,000. We should get 774.6, and it's meters per second because the mass is in kilograms and the kinetic energy was in joules. So this is our answer that we get for the velocity of the cannonball. So I'm going to go ahead and switch back to the PowerPoint because next we're going to talk about the potential energy of and what that means. What is potential energy? So let's go ahead. So what is potential energy? Potential energy is basically stored energy due to an object's position. And there are two main types. So there's gravitational potential energy, which is basically the potential energy due to the gravitational force, whether it's on Earth or Moon or Mars. So basically it's due to the height of the object. And elastic potential energy can be due to the tension in a spring or something like that. But we're gonna not talk about elastic potential energy today. We're just gonna focus on gravitational potential energy. And on the right-hand side, I have the formula for finding gravitational potential energy. So gravitational potential energy is basically equal to the mass times the gravitational acceleration, which is G equals 9.8 newtons per kilogram, which is also meters per second squared, times the height in meters. So potential energy is directly proportional to the mass and the height of the object. And here I have a really quick example just to get familiar with this formula. So here we have a hiker that weighs 70 kilograms, climbs up a hill that is 1,200 meters high. So we want to know, what is the potential energy of this hiker at the top of the hill? So let's go ahead and work this out as well. So I'm going to switch back into the OneNote. I'm sorry for all this switching back and forth. I just think it really helps for writing out these problems. I'm going to go ahead and share the OneNote screen. Okay, so here we're going to talk about potential energy. So let's do this. I'm going to do it in a different color. So potential energy. So here we have, let's just go ahead and write down our formula. It was potential energy equals the mass times the gravitational acceleration times the height. So in this example, it was a hiker who weighed 70 kilograms. So we have the mass, which is 70 kilograms. We know gravitational acceleration because that's just like a constant. So it's 9.8 meters per second squared, or same thing as 9.8 newtons per kilogram. And then we have the height, which is 1,200 meters. And all of these are in the correct units. So when we actually put in the equation, we will get joules for potential energy. So when we plug this in, we get potential energy equals, we're going to put 70 kilograms and 9.8 meters per second squared, and then 1,200 meters. So let's go ahead and multiply these numbers together, and we're going to get 70 times 9.8 times 1,200, and we get 823,200 joules. So This is a pretty big number. Sometimes I like to convert the joules into kilojoules just to make it more reasonable values to work with. So kilojoules is basically there are 1,000 joules in 1 kilojoule. So we could convert this and say, so we have 823,200 joules, and we have 1,000 joules in 1 kilojoule. And it's basically 823.2 kilojoules. So either of these values are the same thing, just different units. Okay, so this is potential energy. It's a fairly simple problem. So I'm gonna go ahead and switch back to the PowerPoint. So next we're going to talk about the conservation of energy. So basically, the law of conservation of energy is the same thing as the first law of thermodynamics, which states that energy cannot be created or destroyed in an isolated system. So that means that energy is basically transferred or changed from one form to another. I'm sorry for the haziness or blurriness for some of these images, but on the right-hand side, if we look at the biker going up the hill, so at the bottom, the biker is moving, but it's on ground level, and so the biker has kinetic energy. But as it's going up, the hill is gaining, the kinetic energy is getting converted into potential energy. And finally, at the top of the hill, potential energy is the maximum in this scenario, and there's no kinetic energy. And then the potential energy from the top of the hill is then converted back into kinetic energy as the biker is moving downwards the hill. In the same scenario, in the different scenario, we have this ball that is being held by a girl, and it is at a top of a cliff, and it has some amount of stored energy or potential energy. But once the ball is released, the stored energy is converted into kinetic energy because the ball is gaining more motion. It's starting to accelerate, and it's gaining more acceleration. So that's when it becomes from potential energy to kinetic energy. So basically, conservation of energy can be transformed in many forms and can be transferred between one form and another. And that's how the law of conservation of energy, or first law of thermodynamics, works. So a big thing that we talk about is the conservation of mechanical energy. And mechanical energy is basically just talking about potential energy and kinetic energy. So those two. So on the right-hand side, we have EM, which is the total mechanical energy, and EP is the potential energy, and EK is the kinetic energy. So we're saying that mechanical energy equals the potential energy plus the kinetic energy. Now, so conservation of mechanical energy is basically saying that mechanical energy is conserved when it's saying that mechanical energy is conserved when the sum of the potential and kinetic energies stay the same. Before and after, or initially and finally. So if you see on the right hand side, we're saying initial mechanical energy equals final mechanical energy. And 1 is for initial and 2 is for final. So if we break it down into its sums of potential kinetic energy, the initial potential energy plus the initial kinetic energy equals the initial final potential energy plus the final kinetic energy. And further down, we can break down each of the energies into their respective formulas, whether it's with mgh or 1/2 mv squared. So this is most of the time we talk about mechanical energy. So, and just to give you an idea, I didn't really write a slide on like conservative and non-conservative forces, but conservative forces include like potential energy, electrical energy, but non-conservative forces include friction or drag, and basically that can be added into these equations to account for like those kind of forces. But in this PowerPoint, we're just gonna, call them negligible because I'm just trying to focus on teaching you about potential kinetic energy and work. So I have an example here. So it's a conservation of energy example. So here we have, there's a golfer on a moon, and on the moon, the gravitational acceleration is 1.625 meters per second squared. And this golfer is striking a golf ball. So as the ball leaves the club, and it leaves the club at a 45-degree angle to the lunar surface, it is traveling at 20 meters per second, both in the horizontal direction and the vertical direction. So it's traveling 20 meters per second in the x direction, and then 20 meters per second in the vertical direction. So that means that the total velocity is 28.28 meters per second. I'm actually going to go through how you can also find that just using the angle and the velocity of 20 meters per second, just so like if you come across a problem like that, you know how to use trig in that kind of way, trigonometry. So we want to find out how high the golf ball will go. So let's go ahead and switch back to my notebook. So this is the conservation of energy problem. So conservation of energy. So here we have our scenario is we're just gonna draw this golf club, okay? This is not a very good golf club, but it'll do. And then we have, it's hitting this ball, and the ball then moves in basically 45-degree angle. Just goes at 45. So it goes. So it's a 45-degree angle here. So in that, let's just say Vx initial. So basically we have the gravitational accelerations. I just want to write down everything I know is 1.625 meters per second squared. And let's go ahead and break down this trigonometry things so you can use this in future examples. So the initial velocity in the x direction is going to be 20 meters per second. And the initial velocity in the y direction is 20 meters per second because that was given in the problem. Now in the problem, it was also given that the velocity, the total velocity initial is 28.28 meters per second squared. But I'm going to go ahead and actually just show you how you actually find this out, you know? So basically we have our x direction value and our y direction value. And we also have our angle. So when we have both sides of a right triangle, so this is a right triangle, both sides of a right triangle that are not the hypotenuse, and we have the angle, one of the angles, we can go ahead and use the tangent formula. So here we can go ahead and say, so we know that tan theta equals the opposite over the adjacent. So that means that in this case, tan of 45 degrees, and using trigonometry is actually very helpful in physics, especially when you get into more advanced questions and all, because usually there is trigonometry. But here we're having tan 45, and the opposite is 20 meters per second. And then here it's 20 meters per second. So this is like what you would find for this formula. But since this is a right triangle, we can actually go ahead and use Pythagorean theorem, since we have two of the sides. So we have a squared plus b squared equals c squared. Let's call vxi a squared, so we'll do 20 squared and plus b squared, 20 squared. And c squared is a hypotenuse, so c squared. We're trying to find c. So let's go ahead and 20 squared, that's 400 plus 400 equals c squared. And then we have 800 equals c squared. And then we get c equals, take the square root on both sides. And we get 28.28. So meters per second. So this is exactly what was given to us as the initial total velocity. So you can use Pythagorean theorem. Now, if you only have one of the sides and an angle, then you would have to use like the tangent formula or the sine theta formula or the cosine formula. But in this case, it was pretty straightforward using the Pythagoras theorem. So let's go ahead and move on with this question. So here we have, I'm just going to write out the conservation of mechanical energy. So here we have EM1 equals EM2. This is always true because law of conservation of energy. So that means that initial potential energy plus initial kinetic energy equals final potential energy plus final kinetic energy. So then let's break each of those energies down into their exact formula. So we have mgh1 plus 1/2 mv. So I'm actually going to change this I into a 1 just because that's how we've written our formula down as. So 1 squared equals mgh2 plus 1/2 mv2 squared. So as you can see, when we were looking at the actual example, we saw that they didn't give us a mass, right? And you might be thinking, oh, I actually need a mass, like it's always in the formula, like I need to plug in mass for the formula. But if you see, if we write it out in this kind of equation, we see that every term in this equation has m. And it's the same object, so m is constant. So since every term has the same m, you can just cancel it out throughout the entire equation. So yeah, so you can just cancel it out. So that's why we weren't given the mass. And most of the time when you do these kind of questions, you don't really need the mass because you can just cancel them out. Unless you plug in some kind of conservative, non-conservative force or something like that. But so here, so let's look at these individual variables. So the initial potential energy. So the height, the H1, so H1 is actually 0 meters because it's starting off on the ground. We're hitting the ball from the ground. So since it's 0 meters, this term just goes away. So it disappears. So we're gonna disappears, right? So it's gonna be simplified into 1/2 m, or not m anymore, 1/2 v1 squared equals gh2 plus 1/2 v2 squared. Now we're trying to find h2. So h2 is what we're trying to find. Since we're trying to find h2, we want to try and isolate that variable. So first, what do? We bring the 1/2 v2 squared over to the left side. So it becomes 1/2 v1 squared minus 1/2. Sorry, I just accidentally stopped sharing my screen for some reason. 1/2 v2 squared equals gh2. Now just to make it a little more simpler, I'm going to pull out the 1/2 on the left side since it's in both terms. So 1/2 v1 squared minus v2 squared equals gh2. So then, now all we have to do is divide by g. So it's going to be 1 over 2. I'm going to actually bring this v1 squared minus v2 squared and put it on top of that fraction and do 2g. That equals h2. So let's see, do I have all these variables? I'm going to write them on the left side. G I wrote as 1.625 meters per second squared. V1 is the total velocity. So we found that to be 28.28, that it was hit from the ground. Now V2, this can be slightly confusing. You may think that at the top where the golf ball will be highest is going to be 0 velocity, but that is not true. So I'm actually going to draw a little bit. So let's imagine this golf ball at the top. So it goes in this almost projectile motion, really. So it's just hit this way. This is a 28.28 meters per second. So at the top, it's not moving in the y direction. So it's not moving up or down because it's at the highest point it can go. So it stops stationary in the y direction. However, the golf ball still has a velocity going in the x direction. So the 20 meters per second in the x direction, that is constant. So that is constant throughout this projectile motion. It is the y direction that is changing as it goes up and then down. But the x direction velocity is always constant. So that is something you would have probably learned in like kinematics with physics. So this is going to be still 20 meters per second. So that's why even at the very top where the golf ball is the highest, it's not moving in the y direction, but it's still moving at 20 meters per second in the x direction. Because potential energy is due to the height. It's not due to the x direction placement. It's due to the height. So it still has kinetic energy, it's just only in the x direction. So this is due to x direction. So we have all our components. So we can go ahead and plug these in. So we have 28.28 squared minus 20 squared over 2 times 1.625. We have to remember it's 1.625 because it's the moon. It's less than 1/6 of the gravitational potential energy as Earth. So let's go ahead and plug those numbers in, and I get 123 meters. So that is how high the golf ball is when it reaches its highest point, starting out with that initial total velocity. So I hope this example made sense. This is a little bit more in depth, and kind of how you apply solving for kinetic and potential energy and how it applies to real life, you know. So it's not just calculating them via a formula. So I'm just gonna head back to the PowerPoint because we do have to talk about work still. So that's our last topic. So let's go ahead. So work. I did briefly mention what work was in the first slide, which is when work is a transfer of energy, or when a force is, or in terms of energy and forces. So first since we're talking about kinetic and potential energy, I'm just gonna focus more on work as transfer of energy. So, but I wanted to briefly mention it in terms of forces too. So work is done when the force applied on an object is in the same direction as the motion of the object. So a usual formula for work in terms of forces is work equals the force times the displacement times cosine theta. So the reason we had cosine theta here is because if you look at that picture below the formula, we have force. It's moving in at some degree, so it's pulling like a little bit to the horizontal and vertically. But the only part of the force that is actually doing work is the part of the force that is horizontal, because the box is moving in that horizontal direction. So basically the vertical part of the force, the vertical component of the force, which would usually be sine theta, F sine theta, that is not doing work. Only F cosine theta is, because the displacement is in the x direction. Therefore, we need to account only for the force in the x direction. And the d is not distance, it's displacement. So basically, distance can be you travel this many miles, and but say you travel 3,000 miles, but you end up doing a circle, so you actually end up in the same place. So you may have done 3,000 miles in distance, but in displacement you actually did 0 because you ended up back at the origin. So, but displacement is how much you are away from the origin, where you started from. So let's just take a look quickly here, like what is work and what is not work in the different scenarios, just to know in terms of forces. So first example, we have this person pushing a box in to the right, let's just say to the right, and also the direction of the motion is to the right. So because the direction of the force is to the right and the direction of the motion is to the right, we are doing work because they're both in the same direction. Now, let's say a person is walking. The direction of the force is upwards because of the normal force on the person. And but the direction of motion is going to the right. So these are not the same directions. The motion and force are in different directions. So therefore, we are not doing work in this scenario. So let's look at something. So that first example with moving the box, that is a type of work that you could relate to kinetic energy. So this third example, though, could relate to potential energy because you're basically lifting this bag of groceries up. So your direction of the force is up, and the motion of the force is up. So that means you're doing work going upwards. However, you're holding this bag of groceries and walking to the side. So your direction of force is up because you're still holding the groceries up there. But you're walking to the right, so you're not doing any work. So this is just to give you an idea of how the direction of force and direction of motion are intertwined together. So let's look at work in terms of energy. So work is equivalent to the change in energy for an object or system. So if work is positive, that means that energy is being transferred to an object. But if work is negative, energy is being transferred from an object. So just to break it down, so on the right side, we have work equals the change in energy. And usually we're just gonna focus on mechanical energy at this point. So work is equal to change in kinetic energy plus the change in gravitational potential energy. And the way you can find the change in kinetic energy is by taking the initial kinetic energy, or final kinetic energy, 1/2 mvf squared, minus the initial kinetic energy, 1/2 mv naught squared. And in the same way, you can do with gravitational potential energy change, where you take the final mgyf minus the initial mgy naught, and y being the height. So this is just how work is in terms of energy. I do have a couple examples on this next slide that are helpful just to give a brief, this is just in terms of energy with work. So let's go ahead and do the first question. So 500 kilograms of bricks is lifted 4 meters above, is lifted 4 meters above the ground. What is the amount of work done on the brick? So let's go ahead and switch into the OneNote. And I'm gonna again use a different color. I like to use different colors. Let's see. So here we're doing work examples. So the first problem, we have this 500 kilograms. So the mass is 500 kilograms, and it's being lifted up 4 meters. The height is 4 meters. So here, there's no motion in the x direction, it's just going up. So here we're actually going to be talking about energy in terms of potential energy, the change in energy. So we know that work is equal to change in energy. And here we're only talking about potential energy. So it's the same as the change in potential energy. Now, change in potential energy is equal to the final height, or the final potential energy minus the initial potential energy. So the final height is 4 meters, but the initial height is 0 meters. And the mass stays the same at 500. So let's go ahead and find this change in potential energy. So we can actually bring out the mass and gravitational potential or gravitational acceleration to make it easier. So 500, and we know that G is equal to 9.8 meters per second squared. And the final is 4 minus 0. So change in potential energy equals 500 times 9.8 times 4 minus 0, which is 19600 joules. And that's also the same as 19.6 kilojoules. And that is equal to work. So this is the work done on the bricks that are being carried up 4 meters. So let's go back to the PowerPoint and see our second question. So our second question is, a 60 kilogram skateboarder is traveling at 10 meters per second on a sidewalk until they hit a wall of bricks and come to a complete stop. How much work do the bricks do on the skater? So I'm going to go ahead. This is our last example. So I'm going to go ahead and draw. It's always good when you're working out physics problems to draw pictures just to evaluate the scenario and what you're working with. So I'm just going to draw this person on a skateboard, and they're traveling at 10 meters per second. And their mass is 60 kilograms. And this is the 10 meters per second is the initial velocity. But they come to this brick. Okay. And so then their final velocity, because they come to a complete and full stop, is 0 meters per second. So we want to see how much work is done by the bricks on the skateboarder after hitting. So in this problem, there's nothing to do with potential energy, just kinetic energy. So work is equal to the change in energy. But in this case, it's the change in kinetic energy. So work is equal to, change in kinetic energy is 1/2 m VF squared minus 1/2 m VI squared. And we can bring out the 1/2 m. So we just have VF squared minus VI squared. So work is equal to 1/2 times 60 kilograms times, so the V final is 0 minus 10. So work is equal to, actually it's equal to negative 3,000 joules. So the reason we talk about negative, because work is transferred from an object. So basically, our energy is transferred from an object. So basically, energy is being transferred from the skateboarder to the bricks because the skateboarder had kinetic energy. So this is the answer for this question. So that was my last example with work. So basically what we talked about was what are energy and work, what is kinetic and potential energy, and the law of conservation of energy, which is first law of thermodynamics, and how you can solve problems using kinetic and potential energy. We did not go into friction or air resistance or drag. That's for another time. And then we talked about how we can view work in terms of forces and energy. And we basically touched base a little bit on forces, but we mainly focused on how you can calculate work from the transfer of energy, as we did in the last two examples. I hope you guys enjoy this lesson. I really enjoyed teaching it. I hope you guys have a good day.